Right. So I was telling you about steroid, cholesterol. Cholesterol is having 8 asymmetric cylinders. Only one structure is representing cholesterol, which is that particular structure that was elucidated by 2 times. First time, it was the proposal was given based on chemical reactions. Second time, the Nobel Prize was given for disproving the earlier one. That is a beauty part of it. That is, the earlier structure was wrong. The correct structure was elucidated later using X-ray crystallography. Okay, so both of these work were given Nobel Prize. Right. So that is. So we were talking. So I was just telling you that I was just telling you about the number of isomers when you have the relationship between the number of isomers and number of chiral carbons. So if you have 2 chiral carbons, there will be 4 isomers. Let us try a compound having this structure. I will put which structure we will take. CH3 HOH OH and COOH. Okay, now see this molecule. So you have one chiral carbon here and here. Both are chiral because you have 4 different atoms and groups here. One is CH3, one is OH, one is H, and the 4th one is this whole group. Similarly, for this carbon, one is OH, the other is H, and the third one COOH, and 4th is this whole group. I hope you can see what I am showing. Now, this will have a mirror image which is non-superimposable. So I can draw this, the second form of this, CS3, OH, H, OH, H, and COH. So this is the second form. What is the relationship between these two? They are enantiomers. Non-superimposable mirror images. Enantiomers. Now I can have a third structure. It's not a mirror image. Look here. What I'm doing is I'm putting the CH3 here. OH, the same place. No, OH I'm putting this way. And here I'm putting retaining the OH on the other side. COH. So what I have done is I have just inverted these two. Okay, one is a mirror image of this. See, this carbon and this carbon are mirror images, while this carbon and this carbon are original. So they are not mutually mirror images as such. Now you can have one mirror image of this. These are the 4 forms of the molecule. CH3, H, OH, OH, H, and COH. So what is the relationship between these two? These two are also enantiomers. What's the meaning? They will be having all the physical and chemical properties the same, except optical activity, chiral, the reactivity towards chiral carbon, and physiological activity. This also will be having the same properties. Melting point will be the same, boiling point will be the same, right? Will be the same. But look at these two. What's the relationship between these two? What is the relationship? They have the same molecular formula, same structural formula, but their orientation in space is different. Okay, therefore you can call them as stereoisomers. They are stereoisomers. Stereoisomers. But they are not mirror images. Okay? Stereoisomers which are non-mirror images. Stereoisomers which are non-mirror images. And they are called diastereomers. They are known as diastereomers. So these two are diastereomers, and these two are also diastereomers. This and this, right? Similarly, these two, this and this are diastereomers. This and this are diastereomers between each other. Okay. So diastereomers are non-superimposable, non-mirror images. Non-stereoisomers which are non-mirror images. They are called diastereomers. Okay. Now, equal mixture of these two will be optically inactive. Similarly, equal mixture of these two will be optically inactive, which you call as racemic mixture. Okay, so D isomer L isomer and DL isomer. DL is the DL mixture, not isomer. DL mixture. Equal amount of the D and L form. This will be optically active with plus rotation. This will be with minus rotation, and this will be plus minus, that is 0. Okay. Now, diastereomers have difference in physical and chemical properties. Their melting points are different. Boiling points are different. Refractive index will be different. Okay, so they are entirely different compounds. Now, so this is a chiral carbon, a compound with two chiral carbons. There is another type of molecule. Again, a compound with two chiral carbon, but with a different peculiarity. Look here. Let me draw a very similar molecule. See here, I'm putting COOH here. All others remain the same. H, OH, H, OH, and COH. Okay. Now this compound is called tartaric acid. Tartaric acid. Okay. Now tartaric acid. Now can you draw all the four isomers of this? Just draw all the four isomers of tartaric acid. Do it quickly. All the four isomers of tartaric acid. I want to do it fast. Just we have drawn above. The same way you can draw it. You can draw it in the same way. On the top I have drawn it. Simple. So let me draw myself. You can check your answers. It is simple. I'm drawing the mirror images. OH here, H here, OH here, and H here. And COH down over here. So this is one. Now let me draw the diastereomers. COOH, H, OH, OH, H, CO. Okay. Now let me bring to you one thing. Oh, okay. I'll finish this and then I'll tell you later. Okay, leave it. Nomenclature will tell you later. Okay, so this is the third, that the one diastereomer. Now this has got one mirror image. This is one mirror. The mirror image of this compound. So I put the OH here, H here, H here, OH here, and COH here. Okay. Now you can see here. Now I want you people to do an exercise like see here. Take this molecule. Take this molecule and vertically rotate it along this axis. Rotate it vertically 180 degrees. Rotate this whole molecule 180 degree and draw the structure. For that purpose, you have to draw this actual structure of this first. What is the actual structure? Let me draw the actual structure. This is the one. Horizontal bonds are pointing towards you. Here also OH. Here H. This is pointing away from you. COH and COH. Now what you should do? COH. Along this axis, vertical axis, rotate this molecule 180 degree. 180 degree rotation along this axis, rotate 180. That is what I told. How will it look like? I told you just now, when you rotate 180-degree, front will come to the back, right will go to the left. That's all. Okay. So this is front. This is the front carbons. They will go to the back side. So see here. I will have the H on this side, OH on this side. Again the same thing here. H on this side, OH on this side. And here these bonds will come to the front. CO. CO. Okay. But remember, this is not this molecule, because this is not a fischer projection. Now what you have to do is along this axis. Along this axis. Rotate it 180 degree again. See, suppose you have this axis, this way you have to rotate. Can you see this? Out of plane. See, this is the axis. Okay, and this is the molecule. This is the molecule and this axis. Now rotate it to the front like this. Just draw the structure. This is what is done with stereochemistry. That is why I told you you have to sit in the class and then do it. Even though it is boring. I know this is the most boring chapter in organic chemistry as far as any student is concerned. Especially this is the case with MSc main chemistry students, BSc chemistry students, all. But unfortunately, this is the most important chapter today. Okay, Tron. So this group will come here and this group will go there. But since they are the same, and again, rotation of 180-degree rotation will bring the front group to the back side. So this will go to. Then this bottom COH also will be going back. Now this group will come here. This hydrogen will come to the top. And that will be different. Back carbon will come to the front. H. OH. And H. OH. Okay. Right. Now compare. Now draw the Fischer projection. This is exactly Fischer projection. This is the exact Fischer projection of the molecule. You can see vertical bonds are backside, horizontal bonds are towards you. So you can draw this way. H, OH, COOH, COOH, H, and OH. See this? Now compare this structure with the first one. See, we have started from here. We have started from here. We are drawing this molecule, mirror image. But the mirror image we have found it is the same as this one. Okay, so to know whether the mirror image is just the same, do you have to go through all this? No, just look here. This molecule is already having a plane of symmetry. See this. Even though it is containing two chiral carbons, it is having an internal plane of symmetry. Internal plane. That means the upper half is an upper half and lower half. They are mirror images of each other. Right? See here, if I keep a mirror here, this is a mirror image. Such molecules, which is having an internal plane of symmetry, such molecules which are having an internal plane of symmetry, in spite of having chiral carbon, they are called mesocompounds. So these two are just the same. So you have only one compound representing this structure. Okay, these and these compounds are just the same. So this is what is called a mesocompound. And mesocompound is optically inactive because the rotation of the upper half is right side, the rotation of the lower half is left side. So they mutually cancel with each other. Mutually cancel with each other. So this is the optical activity of tartaric acid. Okay, so this you will call as one of them you will call as D tartaric acid. This is L tartaric acid, and this is mesotartaric acid. So an equal mixture of these two will be DL tartaric acid. Okay, the difference between meso and DL mixture. What is the difference? Meso is a single compound, but DL is a mixture of two compounds. That means any mixture can be separated into its components. So DL mixture you can separate into two components. But meso cannot be separated into two because it is one and the same compound. Okay, so this is the description of optical activity of tartaric acid. Okay, the tartaric acid is naturally available. It can be isolated from plants and all. Right. Okay, so we will stop at this point for today. Again tomorrow 8:30 we'll meet. Okay, please ask others also to come and participate in the lecture.